So sometimes we need to get rid of functional groups like carbonyl group. We want to remove the carbonyl group from our final compound, and we can just reduce this carbonyl group to get saturated CH2. But sometimes it is also needed that we have to convert this carbonyl functionality to another functionality. For example, we want to make this alkene. So from this carbonyl compound we want to get this alkene. Now how can we get this? So for that there are several reactions, but one of the very important reaction is the Wittig reaction, and this is our today's topic. So Wittig reaction is basically, let's say you have a carbonyl group, a keto, let's say you have a keto or aldehyde. I am just taking keto for example, and you react this keto with a phosphorus ylide. So when you react a keto with this phosphorus ylide, you will get this alkene. Okay, now what is the mechanism? So this ylide you can also represent like this. So you can represent this phosphorus ylide by this separation of this charge, negative charge on carbon and positive charge on phosphorus. And the reaction is basically a 2+2 cycloaddition reaction. So you can write the mechanism like this. Okay, so this 2+2 cycloaddition will first occur, and you will have this intermediate which is called oxaphosphatane. This is called oxaphosphatane, and now this can break in a retro 2+2 cycloaddition like this, and out of that you will get this alkene, and as a byproduct you will get triphenyl phosphine oxide. Now why this retro 2+2 cycloaddition is occurring in this particular way and not the reverse way like this? That you can easily understand because due to the formation of this highly stabilized or high energy phosphorus oxygen bond. So during the formation of this PO double bond, a large amount of energy is released, and this is the driving force for this reaction. Now the question is, how can you make this ylide? So for that, for this particular ylide, you can start from a very simple molecule, let's say methyl iodide or any alkyl halide, then just react with triphenyl phosphine. So triphenyl phosphine will attack here to remove this I minus, so you will get this CH2. I can open 1H. So now here you will have a positive charge. Now due to the presence of this positive charge, this carbon atom is also electron deficient, somehow electron deficient, and that's why acidity will be induced in this hydrogen. So when you react it with a third butyl, let's say butyl lithium. Okay, butyl lithium. So butyl lithium can take this proton to give you this ylide. So you can see this is a very simple reaction. This is a Wittig reaction. Now I will discuss one very important example from csir-net exam, which is based on Wittig reaction, but the problem is a little bit different from normal Wittig reaction. And also two things you have to remember about Wittig reaction is there are basically two types of ylide. For example, let's say you have one ylide like this. Let's say you have a ethyl group here, and here you have a negative charge, you have a positive charge. So for that you have to start from this propyl halide. You have to start to get this ylide, or let's say you can have a methyl group also. So basically you have a R group here, normal R group, but you can have another ylide where you have electron withdrawing group, let's say a star group here. So these two types, these are two types of ylides, and these type of ylides are called stabilized ylide. Why? Because this negative charge is stabilized into this carbonyl group, and these are called unstable ylides. Now when you react these two halides with aldehyde or with unsymmetrical ketones. Unsymmetrical ketone means, let's say you have a ketone where you have one methyl group and another ethyl group, so this is unsymmetrical because two groups are not same. So when you react this type of halides with this unsymmetrical ketones, you will get different outcomes. So for example, let's say you have this methyl and here you have ethyl, and you react it with this unstable halide. So first one I give this number 1, so you react with this unstable halide, so what product you will get? You will get cis. So here you have et, here you have methyl, so you will get a cis product here. Okay, you can see this R group and this ethyl group, they are at the same side, so this is cis product. Whereas if you react it with stable halide, I am giving it number 2, so when you react it with stable halide, you will get trans product. Okay, so this thing you have to remember. Now why this is happening, you can rationalize for the trans product in the second case, because this is a stable halide, that means it has a stability, it has less reactivity, that means high selectivity, and that's why it will give thermodynamically more stable trans product. But why the unstable halide is giving cis product, that is slightly complicated, and the real reason behind this, if we want to see, we have to draw the transition state for the reaction, and I will discuss it in the next video, because that is not important, so important for your competitive exam point of view, but you have to know that, and that's why I will discuss it in the next video. But for now I will discuss a very important problem from the CSIR exam. So you can see this is the problem given. You have given a vicinal dihalide, vicinal dibromide, and this is reacted with first the triphenyl phosphine and then sodium hydride, which will give product A, but which is an intermediate, basically a halide, and reaction of A with this particular compound will give product B. Now we have to identify what are the products A and B. So at the first step, what will happen? So when you react a dihalide with this triphenyl phosphine, the triphenyl phosphine will attack here to give you this compound. Now they didn't mention the equivalence of this triphenyl phosphine, so whether the reaction will stop here or another triphenyl phosphine molecule will attack on this center, that you cannot predict. But after the second step, the outcome will be same in both cases. Okay, so you can get this also, triphenyl phosphine, both triphenyl phosphine can be attached to the molecule. This is possible. But in the second step, when you add the sodium hydride, what will happen? Sodium hydride is basically a base, so it can deprotonate from here to give you this. Okay, now the same thing can be obtained from here also. So you have a hydrogen here and sodium. If the reaction doesn't proceed, so then this hydride can take this hydrogen from here also, and you will get the same thing. Okay, so you will get this thing only. So you can see whether the reaction stops, the first step, that is the attack of the triphenyl phosphine attacks here, or it goes up to there, that doesn't matter, because at the end you will get this only. So this is your product A. Now when you react this with your compound B, with your given compound, this one, what will be the case? Now one thing you have to notice is that this is not a exact halide. Okay, so the reaction will be slightly different. So now you have this, this is called salicylaldehyde. Okay, so this is your salicylaldehyde, and you have this compound. So this is actually like a substrate for 1,4 addition. So this oxygen lone pair can attack on here to give you this intermediate. Okay, Now you can see this this now looks like a elide. You can see, you can also represent it by separation of charge like this. O, this one, and here you have plus, here you have minus, so you can also represent it like this. This looks like a elide. Now there will be that 2 plus 2 cycloaddition step to give you the oxyphosphate. So you will get this one. Okay, now it will collapse to give you the product. Here you have a double bond, so basically this is your product. Okay, so this is your product B you have to predict. So this is a slightly different problem, but based on the Wittig reaction. So I hope it will be helpful for you, and in the next video I will discuss more on Wittig reaction. So thank you for watching, and like, share and subscribe my channel.